Welcome to the world of counterintuitive science, where everything you know about boiling is about to change instantly. Look closely at this water. It is resting calmly at room temperature, appearing completely ordinary in every single way. But watch what happens as the flow begins. Suddenly, a violent surge of bubbles erupts right in the center of the pipe. There is no fire here. There is no heating element. Yet, the water is clearly boiling before our very eyes. This is the mystery of the Venturi effect, a fascinating phenomenon that challenges our basic understanding of phase changes. Let's examine our laboratory setup. This is a clear glass Venturi tube, meticulously designed to manipulate fluid velocity and pressure. Notice the thermometer. It clearly displays 20 degrees Celsius. This is standard room temperature, far below the normal boiling point. Despite the lack of heat, the water inside the constricted throat of the tube is bubbling as if it were on a stove. This isn't just air bubbles. It is the water itself turning into vapor. We call this phenomenon cavitation, and it's powerful. As we zoom in on the narrowest point, the throat, we see where the real magic of physics takes place. Here, the water must speed up to pass through the tight space. This increase in velocity is the key to the mystery. According to Bernoulli's principle, as the velocity of a fluid increases, the pressure within that fluid must simultaneously decrease. In this extreme constriction, the pressure drops so low that it falls below the vapor pressure of the water. When the pressure is this low, the molecules no longer need heat to break free into a gaseous state. They simply pull apart, shattering from liquid into white vapor as they race through the narrowest part of the glass. Digital gauges show the pressure plummeting into a near vacuum state the moment the water enters the narrow throat. This diagram illustrates the relationship perfectly. High velocity at the center equals incredibly low pressure for the flowing liquid. It is a perfect demonstration of energy conservation within a fluid system, moving between kinetic energy and pressure energy. But look what happens just a few inches further down the tube as the glass widens once again. As the water slows down, the pressure rises instantly. The steam bubbles can no longer exist in this high-pressure environment. In a fraction of a second, the vapor bubbles collapse violently, turning back into liquid water as they exit the throat. This cycle of birth and collapse of vapor happens thousands of times a second, creating the turbulent, boiling appearance. To the naked eye, it looks like a chaotic storm trapped inside a small glass tube in a quiet lab. Let's compare the two ways to boil water. On one side, we have traditional boiling using intense thermal energy. On the other, we have pressure drop boiling, where we manipulate the environment rather than adding heat to the system. Both result in a phase change, but the physics behind them are worlds apart, showcasing the versatility of thermodynamics. Understanding these principles is crucial for engineering, from designing boat propellers to industrial piping systems and beyond. It reminds us that temperature is only half of the story when it comes to how matter changes state. Next time you see water boil, remember that a simple change in pressure can be just as powerful as fire. Science is full of these hidden wonders, waiting to be discovered through the lens of a glass tube. Thank you for joining us on this deep dive into the fascinating world of fluid dynamics and thermodynamics. Keep questioning the world around you, because even the most common substances can behave in extraordinary ways. This has been a look at the incredible Venturi effect. Boiling without heat, physics truly is the ultimate magic. Boiling without heat, the power of pressure.